Electrical utilities conductors are designed to carry large amounts of electrical current. They are typically installed outside of buildings. Communication and cable utilities, such as fiber optic cables and coaxial cables, are designed to carry data and video signals. They are typically installed within buildings. Electrical utilities conductors are responsible for bringing much more lighting into dwellings than communication and cable utilities. Consider the fundamental purpose of each utility. Electrical utilities are designed to deliver power, a significant portion of which is used for lighting. Communication utilities are designed to transmit data, not power. The amount of electrical energy transmitted via power lines is orders of magnitude greater than any incidental electrical energy associated with communication cables. The materials and construction of electrical and communication cables further support this. Power lines are thick, often uninsulated conductors designed to carry high currents. Communication cables are typically much smaller and designed to minimize electrical interference. The infrastructure supporting each utility also differs greatly. Power lines are supported by large poles and towers and are designed to withstand significant mechanical stress. Communication cables are often buried underground or attached to existing structures. Now let's look at specific examples. Consider a typical home. The electrical service entrance brings in 120 volts or 240 volts electrical power. This power is used to operate lighting fixtures, appliances, and other electrical devices. The communication service entrance brings in data and video signals. The amount of electrical energy associated with these signals is negligible compared to the amount of electrical energy used for lighting. Furthermore, the design of communication cables minimizes electrical leakage. They are shielded to prevent interference with other electronic devices. The amount of light that could theoretically enter a dwelling through a communication cable is infinitesimally small. It would not be a practical source of lighting. Electrical conductors are sized according to the load they are expected to carry. The National Electrical Code, NEC, provides guidelines for conductor sizing. For example, NEC Table 310.15 B16 specifies the allowable ampacities of insulated conductors rated up to 2000 volts. These ampacities are based on the conductor's insulation type and the ambient temperature. A typical 15-amp circuit requires a 14 American wire gauge copper conductor. A typical 20-amp circuit requires a 12 American wire gauge copper conductor. These conductors are significantly larger than the conductors used in communication cables. The size difference reflects the vastly different amounts of electrical current they are designed to carry. Now let's look at the impact of electrical grounding. Electrical systems are grounded to provide a low impedance path for fault current. This helps to protect people and equipment from electrical shock. The grounding conductor is typically connected to a ground rod or a metal water pipe. The grounding conductor provides a path for fault current to flow back to the source. This causes the circuit breaker to trip, interrupting the flow of the electricity. Communication systems are also grounded, but the grounding requirements are different. Communication systems are grounded to protect against static electricity and lightning strikes. The grounding conductor for a communication system is typically connected to a ground rod or a metal water pipe. The grounding conductor provides a path for static electricity and lightning strikes to flow to ground. The grounding of electrical systems ensures that any fault current will be quickly interrupted. This prevents the possibility of a sustained electrical arc, which could cause a fire. Communication cables are designed to minimize the risk of electrical shock. They are typically insulated and shielded. The amount of electrical current that could flow through a communication cable is very small. It would not be enough to cause a fire. Consider the materials used in electrical and communication cables. Electrical conductors are typically made of copper or aluminum. These materials are good conductors of electricity. Communication cables are typically made of copper or fiber optic. Copper conductors are used for transmitting electrical signals. Fiber optic cables are used for transmitting light signals. The choice of material depends on the application. Electrical conductors are designed to minimize electrical resistance. Electrical resistance is the opposition to the flow of electrical current. The lower the resistance, the more current that can flow through the conductor. Communication cables are designed to minimize signal loss. Signal loss is the reduction in signal strength as the signal travels through the cable. The lower the signal loss, the further the signal can travel. Let's look at the types of insulation used in electrical and communication cables. Electrical conductors are typically insulated with plastic or rubber. The insulation prevents the conductor from coming into contact with other objects. Communication cables are typically insulated with plastic or foam. The insulation protects the signal from interference. The thickness of the insulation depends on the voltage of the conductor. Higher voltage conductors require thicker insulation. The type of insulation also depends on the environment. Conductors that are exposed to moisture or chemicals require special insulation. Consider the installation methods for electrical and communication cables. Electrical conductors are typically installed in conduit or cable trays. Conduit protects the conductors from physical damage. Cable trays support the conductors. Communication cables are typically installed in ducts or trenches. Ducts protect the cables from physical damage. Trenches provide a path for the cables. The installation methods depend on the environment. Conductors that are installed underground require special installation methods. The NEC provides guidelines for the installation of electrical conductors. The NEC specifies the minimum size of conduit and cable trays. The NEC also specifies the spacing between conductors. The installation of communication cables is typically governed by local codes. These codes specify the minimum depth of trenches and the spacing between cables. Now let's examine the safety considerations for electrical and communication cables. Electrical conductors can be dangerous if they are not properly installed or maintained. Electrical shock can occur if a person comes into contact with a live conductor. Fires can occur if conductors are overloaded or if the insulation is damaged. Communication cables are generally less dangerous than electrical conductors. However, communication cables can still pose a safety hazard. Tripping hazards can occur if cables are not properly routed or secured. Damage to cables can occur if they are not properly protected. The NEC provides guidelines for the safe installation and maintenance of electrical conductors. These guidelines are designed to protect people and property from electrical hazards. Local codes provide guidelines for the safe installation and maintenance of communication cables. These guidelines are designed to protect people and property from communication cable hazards. Finally, let's look at the future trends in electrical and communication cables. Electrical conductors are becoming more efficient and reliable. New materials are being developed that can carry more current with less resistance. Communication cables are becoming faster and more versatile. Fiber optic cables are becoming more common. Wireless communication technologies are also becoming more popular. The future of electrical and communication cables is likely to be a combination of wired and wireless technologies. Electrical conductors will continue to be used to deliver power to homes and businesses. Communication cables will continue to be used to transmit data and video signals. Wireless technologies will be used to provide connectivity in areas where wired connections are not practical. Therefore, it is incorrect to assume that more lighting enters dwellings through communication cables than through electrical conductors. The primary function of electrical conductors is to deliver electrical power, which is then used to power lighting fixtures. Communication cables, on the other hand, primarily transmit data and video signals and do not contribute significantly to the lighting within a dwelling.